Hey, geometry, this is now 7.2, thinking inside the box. If you guys did it already, you can check your answers. If not, we'll do it together. So a shipping company makes cube-shaped boxes. Their basic box measures 1 foot per side. They want to know how to scale the box to build new boxes of various volumes. So the original box has a volume of 1 because it's 1 by 1 by 1. So 1 by 1 by 1. The original box has a volume of 1. If the company wants a box to have a volume of 8 cubic feet, what scale factor would they need? So if I wanted the volume to be 8, then the original volume times my scale factor cubed needs to give me 8. And my scale factor cubed is 8, which means my scale factor has to be 2. 2 times itself 3 times is 8. And we could also just do the cube root of 8, which is going to be 2. So that'll give us our answer. If we wanted the box to be 10 cubic feet, so if the volume is 10, the scale factor cube would have to be 10, right? The original volume is 1, times the scale factor cube is 10, so that means K's got to be approximately, let's see, the cube root of 10. Put that in the calculator. Math, cube root, let's do 10. It looks like it's going to be just bigger than 2, not quite 3. So it's about 2.2. Okay. So now for number 3, the company decided to create a graph to help analyze the relationship between the volume x and the scale factor y. So the x-axis is going to be our volume, and the y-axis is going to be our scale factor. So this is our x and our y. So we're going to round to the nearest hundredth if needed. Then on graph paper, plot the points and connect them with a smooth curve. All right, so let's see. If my volume is now 0, what was my scale factor? Well, it's going to be whatever the cube root of 0 is, which is 0. If I have a volume of 1, then my scale factor is going to be the cube root of 1, which is 1. If my volume is 5, the scale factor is going to be the cube root of 5. This one's not going to be such a nice number. If we do cube root of 5, let's see what we get. Math, cube root of 5. It looks like it's about 1.71. Okay. If you have your iPhone calculator, you just hold it to the side. There's a cube root button right there. It's almost in the middle of the phone when you hold it sideways. If the volume is 8, then the scale factor is a cube root of 8. I can do that one in my head. 2 cubed is 8. 2 times itself, 3 times is 8. If the volume is 10, the scale factor is a cube root of 10. We did that a second ago, didn't we? Yeah, the cube root of 10 is about 2.2. I'm going to put it as 2.15 if it's rounding to the nearest hundredth. The cube root of 15. Let's see. Cube root of 15 is about 2.47, about 2.5. The cube root of 20 is about 2.71. And the cube root of 27, that one we can do in our heads. What times itself? 3 times 27, that would just be 3. So now we want to graph it. Now, my x's are going from 0 to 27, and I have, let's see, 4, 8, 16, 20. This will only get me to 20. If I want to get to 27, I'm going to have to count by more than ones. I'm going to count by 2s then. So if I scale, that's going to be 2, 4, 6, 8. So that'd be 16, 24, 32, and 40. I don't think we'll need to go up to 40. We only need to get up to 27. And we're going by 2, so that would be 10, 12. I'm not going to keep going. But my y values, the highest they get to is 3. So if I were to count by ones, I wouldn't go any higher than this place right here. With all these decimals, I'm going to go by, let's see, I'm going to have every 4 be 1. So I'll have that be 1, 2, 3. And so that would make this like a quarter, a half, 3/4. So we'll go by a quarter, or 0.25. And let's graph it. So the 0.00 is on here. So when the volume is 0, the scale factor is 0. When the volume is 1, the scale factor is 1. So the 1 is going to be right between 0 and 2. And we know the scale factor has got to be up at 1. And then we have the 0.5 and 1.7. So 5 is going to be right between 4 and 6. And 1.7 is going to be just below 1.75. The 0.82, piece of cake. 10, 2.75, so 10, and then 2.15, I should say. 2.15 is just going to be right around here, maybe. Right under 2.25 and right over 2.0. When x is 15, the scale factor is about 2.5. So if I go to 15, we're going to be right at about 2.5. And when we're at 20, we get 2.71. So 20, 2.71 is right under 2.75. And when we're at 27, we're going to be at 3. So 24 divided by 27, 3. Now, the way this is scaled, if you were to graph this on something that wasn't scaled, where the y-axis is going up by a quarter and the x-axis was going up by 2s, it wouldn't look the exact same. It'd be like a little bit of a flatter curve. But if I try to smooth out this curve, it might look something like that. And that looks pretty good. So that's what our graph's going to look like. Let's move on. Number 4, the graph shows the relationship between the volume of the dilated box and the scale factor. Write the equation that describes it. So to get our y values, to get the scale factor, we just took the volume and we took the cube root of it, right? So you could think of it as like the scale factor k is the cube root of the volume. Or we can think of it as y equals the cube root of x. Let's just take a quick peek at what that looks like. If I want to do y equals the cube root of x, let's see. I'm not sure if I can do cube roots on this, but the cube root is actually the same thing as raising it to the 1/3 power. So it doesn't look like ours, but it kind of does. We only did it with positive numbers, right? And now it looks very similar to ours, but this is actually scaled correctly, right? Like we had the 0.82 on it, right? And I think 82 is going to be on this one. Yeah. So this is just a more accurately scaled version of it. Because our x's were going up by 2s and our y's were going up by a quarter, it's not going to be the exact same shape, but it looks very similar to our shape. Suppose the company builds a box with a volume of 21 cubic feet and then decides to buy another one with 25 cubic feet. Use your graph to estimate how much the scale factor changes. So let's just use our graph here, right? It says estimate using your graph. So if volume is 21, let's see. 21 is going to be right about here. So it looks like the height's going to be just above this point right here. I don't know. I'm going to say if the volume is 21, then the scale factor k looks to be just above 2.75. Let's call it 2.76 or even 2.78 or 2.8. Somewhere in that range. And if the volume is 25, let's say 25 is going to be right about here. 25, then it's going to be right over here. That looks to be just under 3. Then k is about, I don't know, 2.8. Let's call it 2.9. approximately here. And we could do the cube root to get a more accurate answer. So what's going on here? Use your graph to estimate how much the scale factor changes. So it changes from about, right, because we're approximating 2.76 to 2.9. Or even 2.8 to 2.9, right? So it's not changing much, even though the volume is changing by 4 cubic units. Now use your graph to estimate how the scale factor changes between a box with a volume of 1 cubic foot and 5 cubic feet. All right, so if the volume equals 1, then the scale factor, let's see. If the volume is 1, then the scale factor is 1. We did that one already. If the volume is 5, then K equals, I think we did that one as well. Yeah, it's 1.71. So the scale factor changes from 1 to 1.7. And I guess one thing that's something to pay attention to is that when I change the scale factor, this is the volume's changing by 4 full cubic units. The scale factor changed by barely any, just a little over a tenth of a unit. Here I still changed by 4 units, but now this changed by more than a tenth. This changed from 1 to 1.7. That changed by about 7 tenths. So when you change the volume of small volumes, you have to change the scale factor a lot more. When the volume is changed with bigger number of volumes, the scale factor doesn't change by quite as much. So the rate of change isn't constant, and that's why our function isn't a line. It's not a linear function. So that makes sense. Anyways, that's it for 7.2. Yeah, so we'll do 7.3 in the next video. All right, thanks.